In this video for session 2 of the recorded tutorials for Boulder 2020, I'm just going to go through a binary script, the example and highlight the differences between using a continuous variable and a binary variable. In the first video, I went through in great detail the continuous script and then the ways that we then added in siblings and then changed the way that we specified that model in order to incorporate measured genetic information. I'm not going to go through all of that in this particular recorded lecture, just highlighting the differences between continuous and binary. So I'm going to start off by setting my working directory in case you haven't already done so, clearing my workspace and loading my packages. Again, I'm loading the power function in order to test for power in this model, and that needs to be in the same working directory as so it needs to be in your working directory, this particular file that holds the functions. So when I loaded the data, I loaded actually the smaller data set in order to be able to see some of the power differences between the variables, between the variances, or our ability to estimate A, C, and E. Because when we did this in person, or when we did this in our live session, we had so many twin pairs that we were extremely well powered for A and C, which is not necessarily always the case. So now we're actually going to take our continuous trait and split that up into become a binary trait. Obviously, if you had real data that was continuous, you would not do this because you lose all that lovely detail that you have in a continuous trait, but we're going to do it just for the sake of having the same data for our continuous and our binary example. So we've taken our essentially point of 0, which was approximately the mean. It's slightly under the mean of our continuous trait, and anyone above 0 is going to be coded a 1, and anyone below 0 is going to be coded a 0. And then I can check that. So yes, we have slightly more 1s than 0s, and that is consistent with our means on our continuous trait being slightly above 0. Now, this is the first section that is a little bit different. So this is making sure that the data is an ordered factor. That's what this is doing. And even though our data is coded as a 0 and 1, if our data was coded 1 and 2, we would still have 2 levels. So we'd start at level 0 and then finish at level 1. So you don't necessarily have to have your data coded 0 and 1 to then specify your levels like this. And now we're going to split our data into MZs and DZs. So zygosity 1 is MZs and zygosity 2 is DZs in these particular data. And now we're loading in some objects to make building the matrices later straightforward. This one here is new. This is the number of thresholds. We have only 1. So the number of thresholds is always going to be the number of levels less 1. So we've got binary data and we're going to have 1 less than 2 because we've got 2 levels. So we've got 1 threshold. So here are our variables of interest that we are decomposing the variance of, and these are our covariates that we are going to adjust for. Now here are some start values. There is no mean start value in this particular case, and that's because we're going to fix our intercept. We are not going to, there are different ways that you can specify ordinal and binary data as a model. It's not identified if you don't constrain some elements of this data, because we don't have variance with our binary data. So we are going to, in this particular example, fix our mean to 0 and our standard deviation or our variance to 1, in which case we are mapping our liability threshold distribution onto a standard normal distribution. So this is our matrix that is going to fix our mean at 0. So it's a number of rows is 1, number of columns is in line with our expected variance covariance matrix. It is not free, that is false, and we have fixed the value to 0. And here is our label, and this is the name of the matrix. So now let's set up matrices that are free. These are going to be our covariate estimates. These are our betas, the effect of our covariates. And here are our definition variables that are going to pull in the information about sex and age for each individual in our data set. So data, remember, is specifying a definition variable. And then what comes after the dot is the name of the variable in your data set. You cannot have missing information on a definition variable. If you have missing information, you're going to get an error. And so as long as you don't have trait information on your missing covariate, you can code this covariate that is missing anything you like. It becomes a bit more relevant when you have incomplete families. We have no incomplete families in our simulated data, so we don't need to worry about that. Now, here we have adjusted our fixed intercept with our covariate effects. You could put the covariate effects on the thresholds. In this case, we've chosen to do it this way. It makes no difference really. There's a little bit of interpretive difference perhaps, but we can show with the parameter estimates that you can kind of make sense of things in a very similar way. And if you're interested in looking into the nuances of those differences, then feel free to read up and explore. In this particular case, no, I'll stop there. Okay, so this here is our matrix for estimating our thresholds. This is our number of thresholds, it's the number of rows. This is our number of columns. Again, it's going to match our expected covariance, our variance covariance matrix. This one is free, and we specified our start values up here. And this is a fancy way of giving both thresholds the same label, and we can have a look in that object to see that, which means that twin 1 and twin 2 are going to be estimated to have the same threshold. Now we are creating objects for our A, C, and E variance components, and here we have something different. This is our constraint. So this is constraining our total variance to equal 1, and this object will appear later in order to do that. So now we are creating our variance at the top here, our V, our algebra to create V, which we're going to use in our expected covariance matrix. And then we have our covariance for MZ twins, and then our covariance for DZ twin pairs. And then we're going to put those objects into our expected covariance matrix or variance covariance matrix for MZs and our expected variance covariance matrix for DZs. So our variances are on the diagonal and our covariances are on the off diagonal. And if this had siblings, then we'd need an extra column and an extra row in order to demonstrate the various relationships among each of those pairs. And now we are creating data objects. So we are giving data to MX in the way it wants to receive it and telling MX that we're going to give it raw data so it can cope with some missing values. Here are our expectation objects, which are describing what the model is going to be. Now we have included the thresholds here in this, the expectation of the model. So we've got our variance covariance, we have our means, and we have our thresholds. We could put threshold names in here, but we've not done that. Doesn't matter. And here is our fit function for maximum likelihood. These are our definition variables and our list of variables, and these are all the objects that go into our MZ and DZ models, and our multi-fit function, which is saying, please go get me all of the information across both of my submodels. So we get our log likelihood across everything, our model fit across everything. This is an object so that we can extract easy information later. And this is how we're going to ask for confidence intervals. So we are using this object here in our confidence intervals, and we are going to go get columns 4 to 6 and get confidence intervals on our standardized variance components. So here is our final model, and this is where our constraint is. So we are constraining our total variance to be 1. And let's run it with intervals true. And we have results. So when we have a look at our summary of information, we can see that we have our beta effects. So in our last model for our continuous traits, the beta for sex was 0.25, so it's very similar. Our beta effect for age was 0.17, so again, quite similar. There is no mean because remember that was modeled in the intercept, so it was the combination and is the combination of the intercept and the covariate effects that gives us the expected mean. And the continuous trait had the intercept in our model as about -3.4. And if you think about the expected mean of your dependent variable, your intercept being the expected mean of your dependent variable when your covariates or your independent variables are at 0. So we have age, which is on average 20 in this sample. So when 20 is 0, then that's what actually effectively put our intercept down to -3.4. So now we've fixed our intercept at 0. So it can't move. So our intercept's at 0. We have an age effect that's similar. So 0.15, our average age is about 20. So if we take that up to there, I don't know exactly what it is, but it's about 20. So that puts our expected mean at more like 3. So even though it's mapped to a standard normal distribution of 0 with a variance of 1, when we include our covariates, it shifts where essentially the mean of that distribution is. So it shifts it up to about 3. And that makes a little bit more sense of why we're getting this value for a threshold here of 3. So remember that we split our data at 0, which is approximately halfway through our distribution. And so half of them were zeros and half of them were ones or thereabouts. So we're going to expect our threshold to be around about where that cut is. And that makes sense if we take into consideration these effects of age and sex. So what do these beta weights mean? It means that for a unit increase in age, so for an extra year of age, then you move up 0.15 in the standard deviation of the liability threshold distribution. So you are more likely to be a case by 1.5 of a standard deviation on that latent liability distribution. So moving on to what is sort of perhaps more pertinent, which is the decomposition of A, C, and E. Here we have our variance for A, which is 0.24, a variance for C, which is 0.35, and a variance for E, which is 0.4. And just below it, we have our confidence intervals, and we can see that our A has actually got a lower bound crossing 0. Our C is barely got a lower bound above 0. So had a little bit more trouble distinguishing A and C and getting good power around that compared to our continuous traits. And even our E is not coming out at exactly what our simulated data would expect it to be. So one other thing of note here is that this value in terms of like the number of observed statistics here and degrees of freedom is a little bit out. That's a bug in the current system, which has been identified and will be fixed with the next release. But normally you would be expecting this to be, okay, we have, I've temporarily forgotten how many people are in this, but yes, it would be your observed statistics less your degrees of freedom. So we have, nope, seriously drawing a blank. That's not very helpful, but you can look it up. Okay, so I just wanted to show you the plots of these results running through both the continuous and the binary for the smaller data set that we actually ran through in this online recording. So here we have in blue the continuous, in red, sorry, in orange the binary, and we can see just below it actually put the power in. So this is the power for A in the continuous and the power for the binary. Actually, I didn't run that in the code, but we can do that. to demonstrate that I have copied and pasted those results into Excel correctly. So here we have the power for A. So this is what we get when we we drop A, and we get the difference in log likelihood between the full model and the model without A, and then we weight it by the sample size, and then we run it through the power function that we have in the same folder, and then we do the same for C. So we had 0.33 power for A and slightly better power for C. We had a 0.64 essentially. But when we compare that to our continuous, we had a lot more power for actually, well, C was about the same. Yeah. And again, we had, if you were to go through all of these models and do the alternate specifications by including siblings and changing how zygosity is being handled, when you drop it down to just dizygotic twins and their siblings, then again, we have exactly the same trouble in terms of the model trying to be fitting A and C. There's just not enough information to give it power to be able to do that, even when we had 10,000 families going into this model. So hopefully that's been helpful, and have fun with modeling.